Now let's go ahead and complete our analysis of the runtime of the merge sort algorithm for sorting a list. So we're going to make a pretty restrictive assumption in this argument in order to keep the mathematics clean. And here's that assumption. I'm going to assume that n, the size of the list that I want to sort, is a power of 2. So I'm going to assume that n is equal to 2 raised to the power p for some natural number p. Remember in the last video, I needed to assume that n was even in order for the list to have exactly equal length and not have to deal with rounding. I don't want to deal with that. And so I'm going to assume that n is a power of 2 for some power p. Now, in fact, the argument I'm going to give you, its conclusion, is going to be approximately true even if n is any positive integer. It doesn't have to be a power of 2. But we're going to get the right answer just in this simple case, and then you'll learn how to analyze the more general case in the class on analysis of algorithms. So what do we know already? We know that f of n, the number of steps required to sort a list using the merge sort algorithm, satisfies this recurrence relation. F of n equals 2 times f of n divided by 2 plus n. We derived that in the last video from the merge sort algorithm itself. And then additionally, we do have an initial condition here. So a list of length 1 is already sorted. I don't have to do any computation at all. And so our initial condition is f of 1 is equal to 0. So our theorem describing the runtime of MergeSort is that under the assumption n is equal to 2 raised to the power p, it holds that f of n is equal to n times log base 2 of n. So under this assumption, whenever this list has length equal to a power of p, we actually have this very simple exact expression describing the number of steps. It's n multiplied by the log base 2 of n. And as I mentioned above, this is actually approximately the right formula, even if n is not a power of 2. And when I say approximately the right formula, I mean asymptotically equivalent. The number of steps grows at exactly this rate. But for now, let's prove this theorem under our assumption. Okay, so we are proving a recurrence relation, and so we are going to use induction. So we're going to prove this solution with induction. Proof by induction, so base case. So it gets a little tricky here because we've assumed that n has a specific form. It's a power of 2. And this means that the variable we're doing induction on is actually not n itself, it's p here. And we need to be thinking about the base case and the inductive step in terms of p rather than n, because p specifies n according to this formula, n equals 2 to the power p. So in my base case, I'm going to say let p equals 0. Then I know what's n? N is 2 to the power p. So n is equal to 2 to the 0th power, which is equal to 1. Okay, then let's check our formula here. F of n would be f of 1, which is 1 times log 2 of 1. And log base anything of 1 is always equal to 0. And so we end up with 1 times 0, which is 0. And indeed, that matches our base case that we know for the recurrence relation. Okay, so now let's do our inductive step. And we have to remember that in the inductive step, just like in the base case, we need to assume that the statement is true for some choice of p, And then we're going to try to show that it's true for some choice of one more than that choice of p. So I'm going to assume that the statement, and here, what's the statement? The statement is that this is, the statement is that this is the correct number of steps for my algorithm. We're going to assume that that statement is true for some choice of p. So I'm going to say that p here is equal to h. So here h is playing the role that k usually plays in an induction. I just want to use a different letter so that we don't get too confused. K goes with n when we use that variable, and h is going to go with p here. This corresponds to the choice of n equal to 2 raised to the power h. So our inductive hypothesis, the thing that we've assumed, is that f of n, which is equal to f of 2 raised to the power h, that's our value of n that we're working with right now, is equal to, okay, I plug in 2 raised to the power h everywhere I see an n up here. So I'm going to have 2 raised to the power h log base 2 of 2 raised to the power h. And by log rules, this part, the logarithm of 2 to the power h, simplifies, and it just becomes an h. And so I'm going to have h times 2 raised to the power of h. So that's our inductive hypothesis. Our inductive hypothesis is that the number of steps required to sort a list of size 2 to the power h is equal to h times 2 to the power h. So let's see if we can use this to show the statement for p equals h plus 1. So we'll prove the statement for p equals h plus 1, which means, so I'm going to do the same computation I just did, but I plug in h plus 1 everywhere I see h. And so I'm going to get 2 to the power h plus 1 times log base 2 to the power h plus 1, which is equal to h plus 1 times 2 to the power h plus 1. So this is what I want to prove. I haven't done it yet, but I'm about to do it using some algebra. Computing directly. Here's what we can do. I'm going to start on the left-hand side here. So I'm going to say, okay, f of 2 to the power h plus 1 is equal to my first step. I'm going to use this recurrence relation here. This is often a good first step when I'm using inductive proofs of solutions to recurrence relations. I use the recurrence relation to simplify down. So I'm going to apply my recurrence relation. F of 2 to the power h plus 1 is equal, using this recurrence relation, to f times 2, so 2f. And then I'm dividing by 2 in here, 2 to the power h plus 1, divided by 2, plus n, and remember n is also 2 to the power h plus 1. Okay, next, f of 2 to the power h plus 1 divided by 2, that's just f of 2 to the power h plus 2 to the h plus 1. You know, let's justify some of these steps. So this is my recurrence. That second one is just algebra. But guess what? Now I can use my inductive hypothesis, because I know under my inductive hypothesis what f of 2 to the power h is. It is h times 2 to the power h. So I'm going to end up with 2 times h times 2 to the power h plus 2 to the h plus 1. So that's by my inductive hypothesis. And now I am just doing algebra. So I'm going to take this 2 and put it inside here. So I'm going to get h times 2 to the power h plus 1. And then I have a copy of 2 to the power h plus 1 over here. And if I factor out 2 to the power h plus 1, I'm going to get h plus 1 quantity times 2 to the power h plus 1. And if we compare that to what I wanted to prove, indeed I have done so, and that means my inductive proof is complete. So what we've shown here is that the MergeSort algorithm, this algorithm that takes a list, splits it into 2 equal pieces, and then sorts those and merges the results back together to form a sorted list. We haven't actually implemented this algorithm or even seen how the merge operation works, and so we haven't really done any programming or algorithmic implementation yet. But if we just know something about what it costs to merge the 2 lists, it costs n operations, that's actually enough for us to figure out how much computation we are going to need to do this. In this kind of special case where we assumed that n is a power of 2, we got this exact formula that the number of steps required is n times log base 2 of n. This means that the cost of sorting a list of length n grows a little bit faster than the length of the list itself, but not too much. So it's not n squared or n cubed, for example, but it's also not n. It would be nice if it were n. Unfortunately, it's not. It's a little bit slower than that. It's n times log base 2 of n. This same result, as I mentioned, is true even when we don't make this assumption that n is the power of 2, but it's a little bit harder and more complicated to write that proof.